We see light when we add energy to atoms, and using waves, because light is a wave, we can learn about atoms. Down here at the bottom, I have a sample wave. A wavelength goes from crest to crest. Frequency would be, if I was looking at this wave coming at me, it would be how many crests go by per second. And you should know that the speed of light is always the same, is 3 times 10 to the 8th meters per second. Now, each of these science words has a symbol. So for frequency, we use this Greek letter nu. It kind of looks like a funny looking V. For wavelength, we use a lambda. It looks like a funny looking H. And for the speed of light, we use a C. So you're going to see these in our formulas that we will use. Here's our first formula. It says the speed of light is equal to the wavelength times the frequency. So speed of light is a product of the wavelength and the frequency. So if you multiply those two together, you should get the speed of light. And remember, the speed of light is a constant. It is this number. So let's go ahead and do a problem using this formula. Find the wavelength of a wave with a frequency of 7.15 times 10 to the 14. And then this should read s to the minus 1. You often also see it as a 1 over s, and it is also equal to 1 hertz. And all of this should be on your data tables that are in your packet. Let's go ahead and do this problem. So it says find the wavelength. So the wavelength is this little lambda. And so I'm going to take my formula right here and I'm just going to rearrange it. So I'm going to rearrange it to solve for wavelength. So I'm going to divide each side by the frequency. And so I get wavelength equals speed of light over the frequency. And I can put those numbers in. And for my answer, I get 4.195. And I need to have 3 sig figs. So we're going to round that up, times 10 to the minus 7, and my units, seconds cancels, so I am left with meters. So that is my answer. Please use your exponent key when you're entering these numbers into your calculator. So I would enter a 3, and then my EE button, and then 8. So that means 3 times 10 to the 8th. And then I'm going to press my divided key, and I'm going to type in 7.15 EE 14. So do not use your times 10 button or press times 10 because you're going to get the wrong answer. So make sure you use that exponent button. Let's do another problem. Let's identify what is in the problem. So it says an electromagnetic wave has a wavelength of light at 550 nanometers. So this would be the wavelength. And it says find the frequency, which is a little new, and energy is an E. There is an energy formula. It's right here. This is also on your data sheet. And all of these formulas will be given to you on your test. So you don't need to memorize them. You just need to know how to use them. All right, so let's go ahead and do this one. So first of all, I need to use the speed of light formula because that's the only one that has that little lambda in it. So it's the only one that has that funny looking H, funny looking backwards H. I am going to solve for frequency. So frequency, and then rearranging this, if I divide each side by the frequency, I get speed of light divided by frequency. So I get 3 times 10 to the 8th meters per second divided by my wavelength, which is 500 nanometers. Now look at this, look at the units. The units do not match. This is in meters, this is in nanometers, so you need to get them in the same unit. A quick way to do this is to tack on a times 10 to the minus 9, and that will change the nanometers to meters. So it is not written in scientific notation correctly. To do that, it would be 5.50 times 10 to the minus 7. But you will be given this conversion, 1 nanometer equals 1 times 10 to the minus 9 on your test and also in your packet. And so notice that I just bring that times 10 to the minus 9 down. Make sure you use your exponent button to put this into your calculator. And I get for my answer 5.45 times 10 to the 14. And notice my units, my meters cancels, and I'm left with the unit 1 over S. Now that is the frequency. I could take that and put it into my energy equation right here. So we have energy equals this italicized H. It's known as Planck's constant. He was the one that discovered it. It is given the value that's really, really tiny. This is a number, if you don't put it into your calculator correctly, because it's so small, you can get the right answer. So make sure you use that EE button. So I put it in my calculator, 6.63, EE button, negative 34. And then I'm going to put in my frequency that I just found. Seconds cancel, and I am left with joules, which is an energy unit. And my answer is 3.62 times 10 to the minus 19 joules. So I recommend you get your calculator out and stop the video and make sure that you know how to put this correctly into your calculator. Do both the problems and make sure you get the exact same answer I did. If you get something different, then please come see me so I can help you figure out how you're putting it into your calculator wrong. Now this does say what color is this light, and it is based off wavelength, so 550. And looking on this chart, I see that that is in the green range. So this is a green wavelength of light. It has a frequency of 5.45 times 10 to the 14th hertz, or 1 over S, and it has an energy of 3.62 times 10 to the minus 19 joules. So that one little particle of light has just a really small amount of energy. But this is how you do these calculations. So you will either have the speed of light formula or you'll have the energy formula. And both of those will be on your data sheet, in your homework, and also they will be given to you on your test. There's a video that I'd like you to see. It's done by NASA. It's called The Introduction to the Electromagnetic Spectrum. But we can look at this picture, and I would like to identify where is there high energy, where's there low energy, short wavelength, long wavelength, low frequency, and high frequency. So let's go ahead and put that on here. So looking at this, I have gamma rays on this side and radio waves on this side. I see that as far as the energy goes, this is where there's low energy. Gamma rays have high energy, and I know that because they can kill me. Now let's look at the wavelength. So they tried to give us a little picture here. This is our wavelength here. So we see that we have a long wavelength here, and over here we have a short wavelength. And then we have a high frequency here, and we have a low frequency here. Remember, a frequency is how fast per second each of the wavelengths go by. All right, so what's a direct relationship? So what if something is going up, it also goes, something else goes up, or vice versa. If something goes down, then something else will go down. And we do have two formulas here, and I'm going to just rewrite them. All right, so first of all, I see that this is low and this is low. So that's a direct relationship. Energy and frequency is a direct relationship. So if one goes up, the other one will go up. Because I see on this other side, I have high and I have high. An inverse relationship, that would be energy with wavelength. So as my wavelength gets longer, my energy gets shorter. So that's an inverse relationship. And you also have the same thing with frequency. So as my frequency slows down, then my wavelength gets longer. As far as visible light, humans can only see just a small portion of the electromagnetic spectrum, and the colors range from red to indigo. Roy G. Biv is a little abbreviation to memorize the colors of the rainbow. So red, orange, yellow, green, blue, indigo, violet. Looking at this, which color has the longest wavelength? The longest wavelength I see is the red right here. So it has the longest wavelength. Notice it's measured in nanometers. The shortest wavelength is violet. And so we know that if we have a larger wavelength, we will have a lower energy, and a shorter wavelength, we'll have a higher energy. So it says what has the most energy, that would be violet. So what would have the longest? And then the opposite of which would have the least amount of energy, that would be the red. So applying that to science fiction, which lightsaber has more energy? And you would predict that Obi-Wan Kenobi's lightsaber has the most energy because it's more of a bluish color. Darth Vader's saber is red. It has less energy. So Obi-Wan Kenobi, he should have won this battle because his lightsaber was more powerful. Every element on the periodic table and even compounds, they give off an emission spectrum. White light emits all the wavelengths of light. So if I take white light through this prism, it will split up into the colors of the rainbow. If I were to take that white light and shine it through an element, so if I put my element right here and shine the white light through it, when you take the prism, you would see definite bands right here at the bottom. You would see different bands of color. That emission spectrum, it can act like a fingerprint. It can identify what element you have that's in this gas. So the top colors, that would be like what white light. And if you shine that white light on an element, the element will first absorb certain wavelengths, and which ones it will absorb will be element specific. And then as soon as it absorbs it, it immediately emits those colors. So we can get an emission spectrum. So elements first absorb certain wavelengths of light, and then they emit it. So they won't emit all the wavelengths of light. They're not going to have a smear of color. They're going to have these bands of color. So this poses the question, why do we see different wavelengths of light when we shine light from an element through a prism? And what is happening in the atom? Why is it element specific? What is different about a copper atom versus an oxygen atom? Why do they have different emission spectrums? Why do they have these different wavelengths of light that we can see? Here are some different emission spectra for different elements. So you can see that there are differences. So the top one is hydrogen. So you see a red band, and then there's a whole bunch of bluish and purple bands. When you look at hydrogen, it looks kind of like a bluish purple light. And that's because a lot of its emission spectrum would be more over towards the violet side. When you look at sodium, you're going to see a brilliant yellow light because that's really all it has. Helium, again, looks more bluish, but it looks very different than hydrogen. And then neon gas lights, when you run a current through them, they will glow kind of a reddish orangish. And you can see this from its spectra. And then mercury, which most of our lights in our classrooms and our homes, they have mercury in our light bulbs. You will see this emission spectra. So down at the bottom, I have a sample. So I have hydrogen, carbon, and oxygen all together. So this is my mixture. I can look at maybe a library of elemental spectra to figure out what elements are in this mixture, and I can identify them. So I can see that hydrogen has to have these bands. If it doesn't have those bands, then it's not hydrogen. So looking at this, we can identify it from the mixture. And I can do the same thing for carbon and oxygen, and that's how I know that hydrogen, carbon, and oxygen are in that mixture, because they have every single one of those bands from these three elements. So this one, my mixture, is down here at the bottom. Go ahead and stop the video. Can you find an element that is in this spectrum, in this mixture? Can you find an element that is not in this mixture? Okay, we're back. One of the ones that I do see that is in the mixture is krypton. So every single one of these bands is present down here. And so I know that krypton is in this sample. I do see one that is not there, and that is barium. Barium is not there. And that's because this one band is missing. I don't see anything there. So I know that barium is not there. And you might have come up with a different answer because there's lots of answers for this. But the ones that are there will have every single one of their lines in that mixture. And if just one line is missing, then it would not be in that mixture. We can use this information to look out into space. So we don't have to travel to the sun to know that there's hydrogen and helium that are burning in our sun. That's why we know those two elements are in our sun, is because we looked at their spectral signatures that the sun gives out, and we know that those two elements are in our sun. We can look at different distant galaxies and see if some have water, see if some have carbon. Could there be life on a different galaxy? We could look at the elemental spectra that comes back from us from space to figure out what types of elements are on distant stars or galaxies or different planets. In class, we are going to have an activity where we look at light through a prism to see the different lines. If you missed class, go back in this video and pause it and draw some of the different spectra that I've already shown you. So maybe on your paper, you could draw hydrogen and sodium. So you can just draw those on your paper. Let's go back to this question. Why do we see different wavelengths of light when we shine light from an element through a prism? And what is happening in the atom, the protons, the electrons, and the neutrons? In 1922, Niels Bohr, he looked at these elemental spectra and he related it to the atom. He said it's the electrons that are moving, and they move in a specific way. He noticed that there were energy levels or definite distances from the nucleus where those electrons would be found. And you can only find those electrons on those energy levels. When light is absorbed by the atom, that means that the electron jumps to an outer energy level. So it'll jump from maybe the second energy level all the way to the fourth. When it emits light, then it jumps back down, and it can jump back down in one big jump. Maybe that gives you a purple light, or it can jump back down step by step. So maybe it goes from 3 to 4, that gives me a red, and then 3 to 2 gives me another red, let's say, and then 3 to 1 gives me another red. So again, it can jump all at once, or it can jump energy level by energy level. So Niels Bohr was able to draw his model of the atom. The nucleus is in the middle, and then there's these energy levels around the atom. And we've already talked about these energy levels. These energy levels are distances from the nucleus, and on our periodic table, they are the different rows that we find on the periodic table. So row 1 would be those electrons would be the closest to the nucleus. Row 2, they would be a distance of the second energy level from the nucleus. Row 3, a distance of the third energy level. So Niels Bohr said that when exposed to light, these electrons get excited and they jump to a higher energy level. And this is called an excited state. Almost immediately, they fall back down to the ground state. They can jump what's called a quantum jump and jump several energy levels, or they can do energy level by energy level as it falls back to its ground state, which is the lowest energy level it can be. So these electrons, they absorb all the energy, and then they will release a photon or a wavelength of light, is another way to look at it, immediately. And so we're able to see this light come out of the atom. As I said, Bohr made his model, and it's called a planetary model, and that's because the electrons are going around the nucleus like a planet goes around the sun. These electrons travel in definite circular paths or orbits, is how Bohr described it. They're very mobile, and these electrons can jump to higher orbits. You, however, cannot find them in between orbits. And a good analogy of this is to look at this ladder. You can stand on the rungs, but you can't stand between the rungs. And it's the same thing for these electrons. You can find them at these definite energy levels, but you won't find them in between energy levels. Notice that I get towards the energy levels further away from the nucleus, and you can see that they get shorter or closer together. We know today that the Bohr model of the atom is incorrect. It works perfect for hydrogen that just has one electron, but as soon as you add more electrons with the different elements, you find errors. We still do use it because it explains those energy levels so well, but we have had to turn to a different model of the atom. Today, our model of the atom is called quantum mechanics, or the quantum mechanical model. And it has a lot of math, and this model is based on a supercomputer that Schrodinger used. He looked at the wave nature of the electron and he used math probability to find the location of where an electron is. And he was able to come up taking this equation, and he was able to model that with a computer and come up with something that looks like this. Do you see how it's kind of a fuzzy cloud-like probability? That is where you will find the electron for hydrogen and both electrons for helium. So 1 or 2 electrons will look like this. And Schrodinger, he called it an orbital. So instead of calling it an orbit, it's called an orbital. And this is an electron cloud model of the atom. Now, do we know exactly where the electron is? And Schrodinger said, no, we don't know the exact location, but with 90% probability, we know that it's a certain distance from the nucleus. This is what's known as an s orbital. So it is the closest orbital to the nucleus. Your orbitals do not have to be spherical. So this is an s orbital and this is a p orbital. These correlate with the s, p, d, and f blocks that we find on the periodic table. And these are the orbital shapes. So an s cloud looks like a fuzzy sphere. If this is a 1s cloud, if I were to go out another distance, that would be my 2s cloud. Another distance, that would be my 3s cloud. And I drew a solid line, but it would be a dotted line like you see with the blue. So it's a probability cloud. Your p orbitals, they start with a second energy level, and there is one along the x-axis, one along the y-axis, and one along the z-axis. So this is where you would find those electrons. And you can put 1 or 2 electrons in per orbital. I'm going to quickly sketch out what these probability clouds look like for some of the elements, just so you can get a good sense of what our current model of the atom looks like. So let's start off with hydrogen. Hydrogen is 1s1, and I'm just going to use a solid line, but it would be a fuzzy line. Helium would look the same, 1s2, because I can put 2 electrons in per orbital. Let's go to lithium. Lithium has that orbital, and then it has its own with 1 electron in it. So again, this would be spherical. Beryllium would look the same. Boron, it would have everything here plus its own 2s or 2p1. So it would look like that. After boron is carbon. Now you might think, oh, just put that second electron in that 2p orbital, but the atom doesn't like to scrunch its electrons, so it's actually going to put it in this py orbital. Nitrogen would have all of that plus 1 more, and again, it doesn't scrunch its electrons. It's going to put it in a third p orbital. So on the periodic table, on the p block, we can count 1, 2, 3, 4, 5, 6. So what happens is puts for each of these, they put their electrons in each orbital, and then we're going to go back and make them share. So after nitrogen is oxygen, so it would put another electron in that px orbital, and then go on all the way to neon, where you're going to have 2 electrons in each of the 3 p orbitals. After neon, we have sodium, and it has everything neon has, plus a 3s1. So it would just expand out to the third energy level, and it would be an s orbital. So this is what the model of our atom looks like today. It's all math and it's probability, and we have these different orbital shapes. So again, each of these are called an orbital, and they have a certain shape. You should know how to sketch an s orbital. An s orbital is spherical, and a p orbital, each of them is dumbbell shaped. So you have one along the x-axis, and I kind of run out of room, one along the y-axis, and one coming straight out of the computer screen at you. So those are your 3 p orbitals. This is what the d orbitals look like, so they just get more complicated. So all your transition metals would have these d orbitals. And then here's your f orbitals. So again, these are all their probability clouds, and it's all done with math. So the chances of finding 1 or 2 electrons in each of these orbitals. Here's all of them together so you can see a picture of them. Again, it goes S, P, D, and F. I like this picture right here. It shows what those orbitals look like for reals. So we can see our S. Here's our 1s. Here's our 2s. You can see the 2 layers. And here's our 3s. There's those layers. And then you can see that we have a 2p and here's a 3p. So you can see how they overlap. And then this right here, this is a 3d. Notice that your p's start on the second energy level and your d's start at the third energy level.